Hello, good evening everyone. So we'll wait for some more time, okay? Only two of you have joined. And first of all, am I audible? Can anyone confirm that I'm audible? Yes, okay, thanks for the confirmation. We'll wait for a few minutes, okay? Today is the last session of this live interactive session, so we'll see if others have an interest to join the session, okay? Okay, fine. I think I will get started. If others are joining, let them join between the session. So, in the last class, students were asking to discuss about an example on design spec and one example on optimization. Okay, so in today's class, we'll be no, essentially we'll be covering three topics. Okay, one is the recycle stream, another one is design spec, the third one is the optimization. Okay, for this we'll be using a few flow sheets. Okay, so first we'll simulate some flow sheets. Once after simulation, after which we'll be giving a design spec in one of the problem and giving an optimization in another question. Okay, so I've picked up some simple examples so that we'll try to finish them as soon as possible and discuss your doubts. Okay, so this has been the last session. Okay, fine. So I'm hoping that all of you have Aspen with you. Do you? Can you confirm that you have Aspen with you now? We can perform a simulation. Okay, thanks Harshit. Others? Okay, thanks Arun. So only two of you have Aspen. Others? I think Akshay might be having. Others, do you have Aspen? Okay, thanks. Excuse me. Okay, yeah. What about Adit? Fine. Yes. Last class for the people whoever have attended, we were simulating this process, right? So I'm hoping that you could finish the simulation in the week. There were two students, I think, if I remember, Harshit and Arun have completed during the session time itself, right? So Akshay was the one who said he'll be doing from home. Fine. So I'm hoping that Akshay will have completed this flow sheet. Okay. So, we'll do one thing since there are some new students who have joined to this class. We'll just we'll just hold this flow sheet and we'll pick up another flow sheet. Okay, we'll start a fresh flow sheet. According to the time, we'll come back to this question. Okay. Okay. Yes. So here we have a simple process. Okay. So we have a feed which is mixture of the components which is given over here. Okay. So we have a mixture and then there's a valve and a phase separator which the operating conditions are given over here. Okay, and the bottom product of the phase separator is separated, a part of it is taken as a product and a part of it is pumped back to the incoming, is mixed with the feed. So to without doing the simulation, can you tell me the sequence of the simulation which Aspen does for this flow sheet? Just by looking at this flow sheet, can you tell what is the sequence of Aspen? So let's call mixture, valve and then phase separator, splitter and then pump. So can you tell me what is the order of the simulation performed by Aspen? Just put it in the chat box, okay? And show the flow sheet. So looking at this flow sheet, can you tell me what is the sequence? Anyone? So we have nine of us, right? I think seven of us, two are belonging to me. So seven candidates are attending today's session. So anyone can just tell me the sequence of simulation performed by Aspen without doing the simulation. Okay, I don't want you to do the simulation. Just out of by looking at this flow sheet, can you tell me? So Harshit says it's in numerical order. Okay, so okay, let me just do one thing. Give me a second. What I'll do is I'll give a label to this operations. Okay, it becomes a. So now you have the order, right? Now can you just tell me what is the order in terms of A, B, C, D, and E? Can you put it in terms of A, B, C, D, E? So numerical method. So both Harshit and Arun, which stream are you assuming to be a tier stream in this simulation? Among the 9 streams, which stream are you assuming to be the tier stream? So do you know what do I mean by tier stream? Do you understand the term? Okay, fine, no issues. So Arun says, okay, so it's not only with Arun, it's, if you don't understand what is the definition of tier stream, that's fine, I'll explain, okay. So we'll do one thing, we'll simulate this flow sheet. In Aspen, I'll explain you what is tier stream and how do we change the tier stream and all, okay. So, we'll get started with this process simulation, okay. So the required information to simulate this process is given. You are asked to use RKS shows equation for property calculation, okay. So as of now, just do one case, the 50% case, okay. So the stream conditions and the unit operation conditions are given in the question, okay, in the flow sheet itself. Can you start doing a simulation of the flow sheet given this question? So use SRK equation, okay. So keep me posted your status, okay. I will also do things parallel. So do you think you need any additional information for simulating this flow sheet, or the required information is sufficiently given? Any comment on that? So Arun, you are thinking pump and valve data. Okay, so you can see that the valve, if you see the flash pressure is given over here, right? So if I consider the valve outlet pressure also to be the same and give pressure drop in the flash block to be 0, won't it give me the same result? So this way you can eliminate the pressure of stream 3 to be same as stream 5 and stream 4, okay. So the outlet of valve details are given, okay. And similarly for the pump, no, out of physical sense, you can't mix two streams at different pressures, right? So the feed pressure is at 100 psi, okay. So therefore this stream 9 pressure should also be at 100 psi, okay. So indirectly few information is hidden in the process, okay. However, with our knowledge of physics and thermodynamics, we should be able to figure it, okay. Except the valve outlet and pump outlet details, do you need any further information for this flow sheet to simulate? So the D split data is given over here. See, For the three different cases with percentage of recycling 50%, 25%, and 5%, perform the process simulation. Okay, so as of now, just perform for 50%. Don't worry about the rest too. We'll discuss it. As of now, take it as a 50% split. Okay. And any other information? No more data required, right? Correct. So with the available data, you should be able to simulate this process. Okay, then do the simulation and let me know once you are finishing, about to finish. So. So can you tell me your status? Where are you? Yeah, set up the logs or just give me a status, okay? So how many of you are doing the simulation as of now? We are 10 over here. So among 10, is everybody doing the simulation? Okay, thanks for response, Arun. Okay, thanks, Akshay. RK, not EK. Yeah. So only 2 of you are doing the simulation? Okay, thank you, ma'am. Okay, Harshit, you finished the simulation. That's great. For Mac, I don't think we have an Aspen software for Mac. That's according to my knowledge. Okay. You'll have to wait if your Aspen is not responding. That's the only thing. Or just try restarting it. Just go to Task Manager, close it, and then try opening a new. Is it issue with your system or the software itself? Because others are able to use it, right? So it must be a trouble from your end. Okay, let me also just do it parallelly. So what all components we have? We have methane, propane, right? Then in butane we need to search it doesn't come here. Then the next component is 1,3-butadiene. Right. So the next step after giving components is to select the property method, right? So the property method which is asked is right. Then let's go to simulation environment. So what all unit operations do we have? We have a mixer, we have a valve, we have phase separator, pump, and then a splitter, right? So let us put all those. So we have a mixer, one end. Then we have a valve, then we have phase separator, right? Then we have a splitter, then we have a pump. Okay, there we go. So we have one feed, this comes to valve, this goes here, the outlet comes to switch, right? One is taken as product, the other one goes to pump, and pump outlet goes to this. That's all, right? Did I miss anything? 1, 2, 3, 4, 5. Oh, I didn't put 6 in this. Okay, that's good. Let me use the same convention. That's all, right? So in the feed conditions are given to be 85 degrees centigrade and 100 psi. SIA, and the mass flow is given, right? So its mass flow is 1 per hour, 50, 100, 700, 700, 870, 1176, 5130. That's all. So valve pressure was 25 psi. Right. Then more details are given for the flash. It says 5 degrees centigrade and 25 psi. You can either give 25 psi or pressure drop to be 0. Either you can in fact check. Both of them will give you the same result. Okay. When you specify the outlet pressure in a phase separator, it's a positive value. When you specify delta P a value to be 0, it's considered as a pressure drop. Okay. Now in the splitter, the question asked is about 50%, right? So what additional information do we need to give? It's about pump. So pump discharge pressure is 100 psi. That's all. So the simulation says the input is ready. Okay, let me run this. So let us see the calculation order. Okay, so when you go to the control panel, you can see that it shows the calculation order. Says A, B, C, D, E in the same order which we were discussing few minutes ago. Now, in order for the flow sheet to be solved in A, B, C, D, E order, so if I want to solve A, I need information of the stream 1 and stream 8, right? Without knowing the information of stream 1 and 8, I can't solve stream 1. Why are using Peng Robinson. You can use Peng Robinson as well for this, okay, since it's a mixture of lower hydrocarbons, so no problem with it. So for solving the block A, you need the information of 1 and 8. Without the knowledge of 1 and 8, the A won't be solved. So what Aspen does is assumes some value for 8 and comes back. Okay, so once it assumes 8, it can solve A. After solving A, 2 is known. Thus it will be able to solve this B. Okay, once B is solved, the 3 is known, it will solve C. Now since the 5 is a known stream, it will be able to solve D. So similarly it will be able to solve E. Now it will have the stream details and properties of 8. Okay, so with respect to its initial assumption, it will try matching. It will check whether final output which it has achieved, is it matching with its initial guess or no. Okay, if it is not matching, it will change the value, assumed values in stream A. So how does it reassume? It's the same numerical techniques which we used in the past, okay, using secant method, Weekstein method, or Newton method, based on user defined interest. So the default thing which is used by Aspen, you can see in the convergence block. Okay, so basically assuming something and checking whether the assumption is correct or wrong is known as tiering a stream. Okay, so that's called tier stream. Okay, so in this case our tier stream is 8. Okay, so when you go to the convergence block and check the default options, so default methods, it says for the tier stream it's using Weekstein. Okay, so Weekstein method is used for checking and iteratively updating the assumed value. So you can use Newton method as well, okay, in case if you are interested. Then the tier stream, what does it check? It checks pressure and enthalpy. Okay, so it assumes pressure and enthalpy and it will match iteratively. Okay, and it has got some tolerance. So can we change this tier stream? So instead of assuming 8 as the tier stream, what happens if I assume 3 to be a tier stream? Can I do that? Any comment? What do you think? If I break the tiers 3rd stream, and then will I be able to perform the simulation? Any comment? Okay, thanks Arun. Others? If I assume 3, what happens to the simulation? Will I be able to simulate the process? Okay, let us do one thing. Let us change the tier stream, and then I hope others cut time if you here. So when you go to convergence tier, you will be able to see over. So here you can write which stream you want. Okay. So now let us initialize, save the file, then run. So basically we are forcing Aspen to assume 3 to be tier stream. Okay. Now let us see the order. If you see the order, the simulation started with C. Okay, so it started with C, then went to D, then E, A, B. Let's go to flow sheet and see. So since 3 is assumed, it will start simulation with C, and then it goes to D, comes back to E, okay, then A, then B. Now it will verify whether it's able to match the initial assumption or no. If not, then it will iteratively change. Okay, so that's how that's the basic definition of tier stream. Iteratively match your assumption. Okay, so in a recycle loop, normally in industries what happens is a part of the product is added back to the feed. Okay, so to simulate such a flow sheet, this tier stream or the recycle block is used. Okay, so in this question, is this simulation clear and the tier stream? Could you follow? Could all of you? The definition of tier stream, how do we change it? How Aspen does simulation? everyone? Okay. Okay, thanks for the responses. Now, okay, now the second question in this, which is asked is, now can you change the flash conditions? Okay, basically the flash temperature of this block such that you have a flow rate of 850 lb per hour at the stream 4 using design spec. So since some of you have asked for an example of design spec, this question is framed. Okay. Vary the temperature of the flash such that the vapor flow rate is 850. So you are solving this, right? You are trying to solve the design spec problem, right? Okay. So could anyone finish this? Okay, see here we are trying to find the temperature of the flash, right? So flash is a block, right? Hence we are varying the block variable temperature. So you should select it as a block variable. Okay. However, the flow rate becomes a stream variable. So the target is a stream variable. However, the variable is a block variable. Okay, let me also do it. So all you need to do is go to this manipulators. Okay, then select design spec available here. Okay, just bring it to flow sheet, open that. So we need to define T out, okay, which is what our interest is. So the temperature, sorry, I think I defined it wrong. Our interest is to match the flow rate, right? So it should be flow, sorry. Okay, so our idea is to match the flow rate, right? And the flow rate is a stream variable, right? So stream, which stream are we talking of? A stream variable. Let me just confirm in this flow sheet, it's stream 4 as well here. So the stream, it's stream 4, where we want the mass flow, and the units should be careful, be consistent. It says LB per hour, right? Question asks LB per hour. So we need to specify the flow as 850. Let the tolerance be 1%. So what are we varying? We are varying a block variable, right? It's a flash, it's a block. Okay, and in this case it's C. It is C. What are we varying? The temperature, specified temperature, right? In degree centigrade. Let the lower limit be I don't know, let me put -20, and upper limit, let's say 100. That's all we need to give. Then just reinitialize the problem and run it. Yeah, that's all. It says results are available, right? Then go and check. It says the answer is -4. Okay, so if we want to see which method the design spec is using, just go to the defaults. When you see default methods, it says if you are using a single design spec, it will be using secant method. Okay, you can change the secant method to other methods as well. And once you go to the method options here, if you want to change the secant parameters, okay, based on the maximum flow sheet evaluations or step size, whatever, the methods can be changed. Okay, each method can be changed because some of them will have acceleration parameters as well. So all these things can be given as an input. Okay, that requires bit of just handy with Aspen, that's all. So this way you are supposed to do a design spec. Okay, so could you follow what we did in the design spec? Could everyone follow this? So essentially it's like putting a controller block. Okay, putting a controller block is exactly like a feedback controller. So taking the output and matching the finding the input such that we can match our required output. Okay, so taking the feedback from output, our input variable is varied. Okay, it's like a seesaw system, single input and single output. Okay, here we are varying only one input and getting out only one output. Okay, it's more like a seesaw system. If you want to do a MIMO system, then it becomes an optimization problem with respect to Aspen. There is no controller inbuilt for a MIMO problem. Okay, it's only a seesaw problem. That's all. So could you follow the design spec? Okay, you got a different result. Just check the units in case if you have mismatched it. That could be a possible reason. the stream conditions or something, you would have given something different, or I don't know, if I have given something wrong, then I could also got some wrong result. Okay, it's possible that I might have made some mistake while giving inputs. So just check at your input information. That's the only thing we need to do. Okay. Okay, great. Then you are certifying me that whatever input I gave are proper. Thanks. So others, could you follow? I'm waiting for your response here. Could you follow the design spec? How do we use it? Okay, so do you have any questions still here? I had planned for an optimization problem as well, but I don't think I will be able to start it and then finish it. So I want to know if you have any questions which you want to discuss regarding the course. With respect to exams, you'll get a mail soon. Okay, the pattern and the content, everything, you'll be getting a mail. Okay, so except questions with respect to exam, do you have any questions related to Aspen? Anyone? Any questions? And I kept good time for questions, because this is the last session, so I don't know if you have a good number of questions we can discuss. If you don't have any questions, then we'll pick up the optimization problem and see to what extent we are able to finish it. Everyone? No questions? Okay, then we'll do one thing. We'll do the optimization problem as well. So here we have a multi-stage compression system. Okay, it's a simple thing. So the input pressure is 1 atmosphere to the first compressor. Then we have an intercooler. Then we have a second compressor. Okay, I know that some of you have solved this exercise, but it could be a repeat exercise for you. But for others, it's a fresh one. Okay, so if you have already finished this exercise, just you can practice some other assignment as of now. Okay, so all given over here is 1 atmosphere as input. Okay, and we have an intercooler which is cooling the air to 30, and we have a second compressor. Okay, so the output of second compressor is 40 atmospheres. So we need to find the optimal pressure first at exit of the first compressor, such that the whole compression process requires a minimum work. So how many of you have already solved this problem? No ma'am, we won't be having any more sessions. This is the last session. Okay, so okay, Arun, you didn't solve. Others, did you solve this multi-stage compression example? Arun, you can go ahead with this. Okay, in case you are not solving, just try doing it. It's based on optimization. Okay, it's air. Okay, so yeah, okay, let me show you the question. It's dry air. Okay, it's mixture of nitrogen, oxygen, and argon. Okay, let me also specify the composition. I'll put it in the chat box. Okay, 78% of nitrogen, O2, it will be around 21%, and rest is argon. Okay, yes ma'am, I'll be sharing my email ID towards the end. Okay, you can just mail me if you have any questions. Use Peng Robinson. Okay, PRUS. also do parallelly. So we have two compressors and an exchanger, kind of a cooler in between. So we have one stream coming in, the compressor, and then a cooler, and then another compressor going out, right? So let's assume it's 300 Kelvin and 1 atmospheres. Let us take one. That's mole fraction. This is 78 V1 and 0.01. First compressor, let's just guess the value as of now. Any other information given? Yeah, 75%, right? And B2 temperature, it says 30 degrees. Pressure drop is 0, right? Compressor. Discharge pressure is given to be 40 atmospheres and 75%. So that's all required information for simulating the flow sheet. Okay, let me also see. So what we are supposed to do with respect to optimization is, first we need to create a calculator block which calculates the network for us. Okay. So we define the first compressor work, the second compressor work. So it's a block variable, right? The first compressor work, and it becomes an input variable. Block variable, and it's B1 network. And W2 block variable, block B2 network, and it's an import variable. We need to export the network. So it becomes an export variable. Let's go down, steam utility, it's a parameter. Let us give the number to be 1. What are we calculating? W net, W1 plus W2 also. So a calculator block is ready which calculates the network for us. So if you see for the case which I gave 5 atmospheres, so it says the network is 4.5 kilowatt. Right? The next thing which we are supposed to do is go to model analysis tool, click on optimization, new. So we need to define work over here. Okay, so it's the same. We should be consistent with what we gave. Okay, we are calculating network in the calculator block and bringing it here, basically exporting from the calculator block and importing in the optimization tool. Okay, so in the optimization we'll say it's a model utility and it's a parameter which is valuing 1. Okay, now we need to minimize the work, right? This is an unconstrained problem. We don't have any constraints. So what variables do we have? We need to vary the block variable, which is block 1 pressure, right? Let be consistent with the units. Let the lower limit be 2 and upper limit of I don't know, let's put 20. Save it and then run. So we have some result. So it says the optimal value is 7.05 bar. Okay, so essentially it calculates works of different both the compressors, then brings them. Okay, so if we want to verify how this work of compressors vary with respect to the intermediate pressure, you can do a sensitivity analysis. Let me do an additional thing. Okay, just create a sensitivity analysis. So we'll vary the intermediate pressure. Okay, it's a block variable, it's B1, its pressure. Let me vary in atmospheres. Let us take from 1.2 to it was 40, right? So we'll take 39. Okay. Increment of 1 atmosphere. Or let me put from 2 so that the graph comes a bit better. So what do we define? W1, W2. Okay. So W1 is the first block network, and W2 is the second block network. And also let's put W3 or the WNet. So what do you tabulate? Just fill all the variables. Let us run this sensitivity analysis. I should have deactivated this optimization. We can actually first let's delete the network and then run it. Okay, we have some results. Let us plot this. On x-axis we have variable, on y-axis let us plot the two works. So with respect to the intermediate pressure, you can see that the one of the compressor work, the first compressor work is increasing, whereas the second compressor work is decreasing. Okay, so since one of the compressor work is increasing and another one is decreasing, when you consider the network, it will be like a parabola, right? Inverted parabola. So the network goes through a minimum. Okay, so that's how we get we solve an optimization problem. It's like trade-off between two. So when we are trying to increase the intermediate pressure, the first compressor work is increasing, whereas the second compressor work is decreasing. So there's an optimal point for which our overall work will go through a value. Okay, so it goes through a deep and then goes up. So we are trying to identify that location which minimizes our overall work. So that's what we do in the optimization. So whatever I did, is it fine? Could you understand? The answer remains same irrespective of the feed flow. Okay, whatever you can take, just 1 gram per second or 1 kg per second, your final value will remain same. It's independent of the feed flow. Could you follow what we have discussed on optimization? Leave the sensitivity analysis part, it's a different thing. I wanted to show those graphs, so I created a sensitivity analysis. Okay, yeah, you can watch it again. Anyways, this lecture is getting recorded, so it will be available on YouTube in quite sometime soon. Okay, that's great. So do you have any other questions which we can discuss now? Any reference for biogas simulation? No, yeah, I don't know. I shouldn't tell from half knowledge. No, I don't have. But just put your mail ID in the chat box towards the end of this lecture. If I find one, I'll just mail you. Not now. Okay? Once I stop the recording, then just put your mail ID. Any other question? Okay, continuing Aspen education. Mhm. Let me just stop all this recording.